Okay. Hello, everybody. Sorry about that. Please come on in and take a seat. We're going to get started in just a minute here. So it's my pleasure today to introduce Kevin Novan, and he's an assistant prof in agricultural and resource economics here at Davis. And Kevin joined the department in 2012, and his research interests are in the field of energy and environmental economics, focusing primarily on questions surrounding the design and implementation of policies targeted toward the electricity sector. And so his recent work quantifies the impact of renewable energy on pollution and examines the social costs and benefits of storing electricity and evaluates the energy and pollution savings provided by residential electricity efficiency investments. So, Kevin, pleasure to turn it over to you.
How's that? Okay. Thank you all for coming. I appreciate it. I'm going to warn you right off the bat, after you heard that little spiel about me, nothing in there had the word transportation in it. I'm going to focus on the electricity sector in this presentation, but I'm going to do my best to highlight how the lessons I'm trying to point out in this paper, in this project, are directly applicable to those of you interested in transportation policy in terms of electric vehicles. Okay? Let's jump right in. If there's questions too at any point in it, throw your hands up, let me know. Okay? Happy to go. All right, so there's a ton of policies that are directly designed to either directly or indirectly designed to basically reduce pollution. And those are all effectively targeting the electricity sector, the ones I have in mind. So you can think of this as we have policies pushing electric vehicles, so subsidies for electric vehicles. How much pollution is actually saved by using electric vehicles versus a conventional vehicle? That's an important question to know if we're going to evaluate those policies. There's certainly a lot of subsidies for energy efficiency, energy efficient appliances, weatherizing your homes. How much pollution are those policies actually saving? That's a really hard question to answer, as it turns out. The one I'm going to look at in this project is, what about when we generate electricity from a solar panel or a wind turbine? How much pollution is actually being reduced from that? Right? We need to know those if we're going to actually design policies that are intelligently supporting these different technologies. So in practice, the way we've looked at trying to estimate the pollution savings or the pollution caused by, say, plugging an electric vehicle is the strategy of estimating marginal emission rates. What is a marginal emission rate? So essentially the idea is, look, if you plug in an electric vehicle, you're increasing the demand for electricity by a little bit at that point in time. Okay? Alternatively, if you're generating electricity from a wind turbine, when those blades are spinning, you're generating a little electricity and reducing demand for electricity a little bit at that point in time. Well, now the trick is to just say which conventional generators are either increasing or decreasing their production at that point in time in response to that plugging in an electric vehicle or in response to that extra power coming from a wind turbine, right? That technology that's on the margin, we want to know what that is, what's the emission rate or the pollution rate of that technology. That's the marginal emission rate. If we know what that is, then we can say, well, how much pollution was caused by plugging in an electric vehicle? Or alternatively, how much pollution was avoided by a wind turbine or a solar panel? Okay? That's really all we've done in this literature so far. We're essentially taking the estimates of that emission rate of the marginal generator and multiplying it by the change in the amount of electricity we're either demanding. So say you're plugging in an electric vehicle, how much extra electricity are we demanding at that point in time? And what was the marginal emission rate? There's our prediction of how much more pollution is created to charge that vehicle. If it's a wind turbine, how much extra wind generated output are we producing? What was the emission rate of the technology that would have supplied that electricity? There's how much pollution we avoided. Seems very intuitive. I like this. This is a good way to evaluate these policies in my mind, and I'm happy to chat more about those. But I'm going to have a big argument with this approach, and that is we've completely ignored the fact that when we're talking about energy policy, we don't use one policy at a time. We're not just subsidizing electric vehicles. We're not just subsidizing renewable electricity. In particular, in the case of the electricity sector, we directly regulate the amount of pollution that can come out of our fossil fuel generators. We do that for specific pollutants. So we have a cap and trade program in place for CO2. In other parts of the country, we have cap and trade programs for NOx emissions or SO2 emissions. So we've limited effectively, in some cases, the amount of specific pollutants that we're going to let go up into the air. We really have to focus on that if we're going to try to evaluate what are the benefits then of wind turbines or solar panels, or alternatively, what is the pollution that's being created by charging an electric vehicle. So intuitively, if we put a binding, a cap that is limiting how much pollution we can emit for a specific pollutant, that cap is in place, we charge an electric vehicle, or if we produce a little extra electricity from a wind turbine or a solar panel, we're not going to change the aggregate amount of that cap pollutant that will ultimately be emitted. We're going to use up all of those pollution permits. Okay? So here's my question then. What in the world are we doing to all the other pollutants then? What about all of the other pollutants that we're not directly regulating with the cap and trade program? How are we affecting the emissions of those by charging an electric vehicle or producing renewable output? That's what I want to look at in this project. Okay? So just to give you the really quick overview in case you take nothing else away, here's what I want you to learn from this. Okay? I'm going to show you the simplest of simple little theoretical models. And like all good economic models, all it takes is just moving a couple lines around to get the intuition. That's all we're going to look at, okay? I'm going to show you in a very simple setting, I'm going to focus on electricity, but this lesson is applicable to electric vehicles and other settings. I'm going to show you that if you produce more renewable electricity, so if you install more wind turbines, more solar panels, and you've also capped the amount of a specific pollutant, the cap and trade program, then it's very likely that increasing that renewable output would actually increase total pollution. Totally counterintuitive to what we'd expect, totally counterintuitive to what our estimates have been saying, that wind turbines, solar power, it's got to be reducing pollution. It might not. Okay? And it's because of the way the policies interact. I'm going to look then at a specific cap and trade program that was in place in the eastern half of the US. It's a cap and trade program on the amount of NOx that was emitted from fossil fuel generators. And I'm going to just run with a little thought experiment. I'm going to say, if that cap was a binding cap on NOx, what would have happened to the annual emissions of CO2 and SO2 if we installed more solar panels? I'm going to hopefully convince you that sure looks like we would have increased SO2 emissions by adding more renewable electricity, and we would have reduced some CO2, but by a lot less than the entire kind of marginal emission rate literature would suggest. Okay? So here's how this is really applicable to electric vehicles. I could take the same intuition that I'm going to show you and flip it around. There's been several papers that have come out showing, using the marginal emission rate approach, that when you plug in an electric vehicle, well, if you're plugging it in overnight in a lot of places, you're going to be charging your car effectively with coal that's on the margin in a lot of the country. So therefore, it looks like charging an electric vehicle creates a lot of pollution. What is that missing? Well, if those areas of the country where you're charging your car also have a cap and trade program in place, you're not increasing the amount of that cap pollutant. And in fact, the same intuition I'm going to show you would argue that charging that electric vehicle reduces other pollutants coming from the electricity sector in that area. So in that sense, even without offsetting gasoline, I'm going to argue that an electric vehicle reduces pollution just by charging it. Really counterintuitive, okay? Hopefully this will make sense when we start moving some lines around, okay? just to get the notation out of the way. I promise there won't be math after this one, okay? In this really simple model, I'm going to think of just a single period. I don't want to think of multiple time periods. We consume electricity and generate it in one period, okay? And I'm only going to consider two different forms of kind of conventional generation. So electricity can be produced from coal or from gas, okay? So those are the technologies that can increase or decrease their output on command. And I'm also going to assume that there's two different pollutants that come from these different generators. Okay, so you can think of that as the regulated pollutant. And in my setting, when I start looking at the cap and trade program, that would be NOx. That's our regulated pollutant. And then the other pollutant would be CO2, okay? The unregulated pollutant. Then there's going to be some totally exogenous demand for electricity. D is just how much we're going to consume no matter what. It's not responding to prices or anything like that in this simple model. And R is the amount of renewable output, the renewable electricity that just gets generated because that's how sunny it is or how windy it is. Okay? So what does this look like? Well, in a very simple case, X1 was the amount of coal-fired generation. X2 is the amount of, say, natural gas-fired generation. Okay? This line right here is what I would call the residual demand. That's the difference between how much we're demanding, how much electricity we want, and how much is being supplied just by the wind turbines or solar panels or whatever it is feeding electricity into our grid. The amount of coal and gas generation has to put us somewhere on that line. We have to exactly have the amount of electricity we're producing equal how much residual demand there is. Otherwise, grids melt down. Okay? So intuitively, where would we be if there was absolutely no regulation whatsoever? It'd be at the lowest cost point, the lowest private cost point on this. So one way to think of that would be, well, coal's a little bit cheaper than gas in most of the country. Maybe I can still make that statement. Okay. So we'd be at a bundle perhaps where we get a little bit more X1 than X2. So this point right here would be our equilibrium outcome. That's how much fossil fuel output we would get if there was no regulation whatsoever. Make sense? So what happens if we put a cap and trade program in place for one of these pollutants and it's a binding cap? We're going to push ourselves away from this point. I called this coal, I called this gas. Well, that makes sense then that we're going to have to push ourselves probably towards the cleaner fuel that we think, gas, right? So this red line is going to be my cap. This red line is showing you every point on that red line has the same amount of this capped pollutant that would be emitted. We could produce the limited amount of that capped pollutant by using just a little bit of coal-fired output because coal's really dirty. Or we could produce a lot of gas-fired output and get the same amount of pollution. We need to be somewhere on or inside that red line, otherwise we're going over the legal limit of that pollution. So where are we going to end up? Well, we can't be here. That cap and trade system pushes us up to point A. Okay? So there we are. That's our equilibrium outcome. That's what would happen with the cap and trade program. And now we can use this super simple little framework and say, what happens if we now flood the market with more renewable electricity? Okay? And I'm going to break down the changes that occur into two different steps. Okay? So if we increase renewable electricity, so R gets bigger, the residual demand curve just shifts back. We don't need to produce as much from coal and gas anymore. Okay? The very first step that I'm going to think of would be, well, right when that wind power or solar power gets produced, we're going to reduce some coal and some gas generation. Weekly, a little bit of both. Okay? I'm going to call that first change that occurs as this movement from A to B. You're going to reduce how much coal and gas output you produce. That's my scale effect. Is the cap still binding at point B? No. Now all of a sudden we're at a point where we have spare pollution permits sitting around. So what should happen to the equilibrium price of those pollution permits? It should go down. And as the price of those pollution permits falls, what should happen? It should keep falling until we get back to the point where, if this is going to be a binding cap, we're using them all up again. So we're going to shift along this new residual demand curve to this new point C. I'm going to call that the composition effect. So I'm not changing the amount of fossil fuel generation as we move along that line. I'm just changing the relative amount of gas to coal that occurs. Does this make sense? So what have we done? By adding renewable electricity, we actually went from this amount of coal to a higher amount of coal, this amount of gas to a lower amount of gas. We did nothing to the level of the capped pollutant. We're still emitting the same amount of that capped pollutant. What did we do to the unregulated pollutant that's floating around now is the question. Okay? So I'm going to think of two different cases. Here's the first case, which is totally fictitious, and I'll point out why. This is the level curve for this other pollutant, the unregulated pollutant. Every point along this blue line, we're emitting the same amount of, say, CO2. Okay, so this is the amount of CO2 we would have started with prior to adding that renewable output. Okay. This slope is a lot flatter than this slope. What that means in this setting is the technology that has a higher emission rate for the unregulated pollutant actually has the lower emission rate for the regulated pollutant. I said that was totally fictitious because that's not true. Right? That's not how we actually would think about our fossil fuel generators. In reality, a plant that has higher CO2 emission rates, on average, will have higher NOx emission rates and higher SO2 emission rates. Not necessarily, but on average. So this correlation isn't very realistic. But if we were in this really ideal world, what would happen to that unregulated pollutant as we add more renewable output? Well, the scale effect has to reduce pollution because you're reducing some coal and gas output. Great. What about the composition effect? Well, as those pollution permit prices fall, we should reduce even more of that unregulated pollutant. So in this case, we should get a really big reduction in the unregulated pollutant. This would be a case where I would say a subsidy for renewables actually makes a great deal of sense. Okay? But this isn't a very realistic example. This other case is much more realistic in my mind. The technology that has the higher emission rate for the regulated pollutant also has the higher emission rate for the unregulated pollutant. Coal is dirtier in terms of its CO2 emissions and its NOx emissions. So in this setting, what happens? Well, if you increase renewable output, you're going to shift back with the scale effect to a lower level of the regulated pollutant. You've reduced some pollution, it looks like. But as you increase the share of coal to gas, as those pollution permit prices fall to get us back to the equilibrium, you've actually kicked back up to a higher level of this unregulated pollutant. So in your effort to try to do something environmentally friendly, darned if you don't actually increase the emissions of the unregulated stuff without doing anything to the regulated thing. Does that make sense? There's tons of assumptions in this simple little setting, right? But this is very intuitive, and what I want to point out is the marginal emission rate literature that I pointed out in the very beginning of this paper. All we're doing with that approach is saying what was on the margin when wind or solar output was produced. And therefore, all we're doing is estimating this scale effect. So all of the estimates based on the marginal emission rates in settings where there's a binding cap have completely ignored this shift from B to C, and therefore it's not clear what we're even estimating sometimes. Does that make sense? So now I want to say, is this even possible? Is it possible that we could have solar or wind, for example, increase pollution? And to do so, I'm going to look at that specific market that I had mentioned earlier, the cap and trade program. It's called the CARE program during the years I'm going to look at it. Okay? Effectively, all of these states in highlighted area here had effectively two different pollution caps for NOx emissions from their big industrial sources or from their power plants. Okay, I'm going to focus on the power plants. Two caps. There was one that capped the annual emissions of NOx, and then another one that capped the ozone season emissions of NOx. And that ozone season is specifically May through September. October out here, but I think May, September on the East Coast. I think I got that right. During the hot summer months. Okay, why is that? Well, NOx during the summer, when it's emitted, mixes with more volatile organic compounds and a lot of sunlight, creates ground level ozone. And that's a big problem specifically in the summer in the US. Okay? So that's why we had this stricter cap that took place during this middle part of the year. I'm going to use that fact later. Ignore that for now. Okay? Because the thought experiment I want you to think about would be, if that annual cap on NOx emissions was really binding, and it turns out during the later part of the sample it wasn't, that's why I really want to think of this as a thought experiment, okay? If we really did put a binding regulation in place, what happens if we add 1,000 megawatts of solar capacity to a different region in this area? What are we doing to NOx? Well, I would argue nothing, right? Because it's capped. But CO2 and SO2 were effectively unregulated in this time period throughout this entire region. So in that case, what's happening to those unregulated pollutants? Are we in case 1 where we're reducing them, or are we in case 2 where we're actually increasing them? Okay? I'm going to tackle this with the best data I can come up with. Just tell me what you think when we're done. How about that? Okay? So here's what I have. I have first, simulated output from solar panels. There's nothing magical about this. I'm just observing solar generation that exists, and I'm saying, well, I'm assuming the new solar panels that we would install would produce very similar patterns. It's sunny during the middle of the day. Nothing magical there. So I'm going to estimate then just what would the hourly output from these 1,000 megawatts of added solar capacity be? The other data I'm going to use comes from the EPA's SEMS data. So what they do is they actually record the generation and pollution that comes out of effectively every fossil fuel generator in the country. Okay, so I'm going to use all of the fossil fuel generators in everything other than the west region. Okay, so this entire area here, the Eastern Interconnection and the Texas Interconnection, those are the areas that are directly regulated by this cap and trade program. So here's the basic intuition behind the empirical strategy I'm going to take to say what would be the impact on pollution. Just like the theory model showed, there should be two distinct effects. There should be a scale effect. You add renewables, you're just going to reduce coal and gas generation. Okay, what's on the margin and how much pollution gets offset? That's the scale effect. Then the second thing I'm going to try to do is estimate what that composition effect would actually do. In other words, as NOx permit prices have to fall to get back to a binding cap on NOx, what would the change in CO2 and SO2 be that results from that? Okay? And hopefully I'm going to show you some somewhat convincing evidence that this composition effect for SO2 would be huge. We'd see a shift away from gas towards coal, which would make a big increase in SO2, which would completely swamp the scale reductions in SO2. CO2's composition effect wouldn't be quite as large, so in the end, the scale reduction in CO2 would still exceed the increase, but if we ignore this, we're going to completely overstate the environmental benefits of, say, solar panels in this region then. Okay? Okay. Very good question. So, two parts to this. Let me first say, not only did I totally ignore how they were allocated, so whether there was an auction for the permits or whether they were grandfathered out or based on some historical pollution, I'm ignoring that. I'm also assuming in that simple theory model that it's a competitive market. Perfectly competitive, in fact. And ultimately, if we assume that this electricity sector is competitive, then it doesn't matter how these things are allocated. It doesn't matter if you grandfather permits, and that is just give the firms the permits which allow them to pollute, or make them pay the government through an auction for the right to pollute. You should end up at the same ultimate and equilibrium level of pollution from the different fossil fuel generators. So I'm being totally agnostic about effectively how these things are distributed. More importantly, I'm being very unagnostic about my idea behind whether this is a competitive market or not. Right? A monopolist versus a competitive firm would behave very differently when exposed to a cap and trade program. So that's a well kind of driven home point. I would argue that the electricity sector in many parts of the eastern U.S. is very competitive, and in other parts of the eastern U.S. it's very much a regulated monopoly. And in perfect competition is a really bad assumption there. Okay? So that theory model is specific to perfect competition. The empirics I'm going to show you, I'm just going to be totally agnostic about all of that and just say, what is the data saying the scale effect would be, and what is the data saying the composition effect could be? Does that answer somewhat sufficiently? Okay. I'm going to use two massive assumptions, and I want to make sure that I'm up front with these, okay? First, the scale effect, which was you add some renewables somewhere, you're going to reduce some fossil fuel output. I'm going to assume that if you add the renewable electricity to the Texas region, you're only going to directly offset fossil fuel generation in the Texas market. Similarly, I'm going to say if I had instead installed that solar output up here in, say, Ohio, I'm only going to reduce fossil fuel output in this NERC region. That's wrong. That's not a good assumption by many people's standards, right? And that's because if I add renewable electricity here, well, this grid is connected to this region. So electricity could be offset elsewhere too. Okay. So the results I'm going to show you impose assumption one. It doesn't matter in the end. I've tried relaxing that assumption, I guess. So just go with it for now. I want you to see that's the results I'm going to show you. It doesn't end up affecting anything. The second assumption, this is another big one that's common in this marginal emission rate literature. So anytime you're reading a paper that tries to estimate how would charging an electric vehicle affect pollution, they have to take a stance on both of these assumptions. Okay. The second assumption is, I'm going to assume that only fossil fuel generators are being directly offset when we add renewable output. Or in other words, I'm assuming only gas, coal, or diesel generators can be on the margin. Okay? There's a bunch of other sources of electricity. Nuclear, right? Nuclear produces a reasonable chunk of our electricity. But it has such a low marginal cost of production that it doesn't make much sense to think that, well, look, the solar power increased today. I'm likely going to start ramping down my nuclear plant. Their base load power, they produce whenever possible at full. Okay. Something like hydro, that could be a problem. I'm happy to have this philosophical debate offline because we can go for a long time on this one. Hydro generation is certainly not a zero marginal cost. There's a big opportunity cost to using your hydro power. If you spill the water over the dam or if you throw it through the turbine and use it, that's less water you have to produce hydro output later. That's a cost. That's an opportunity cost. I'm assuming that that hydro is not going to be responding to the solar output I'm simulating in this case. Okay? Happy to chat about that one more. I think those are both really interesting questions that the marginal emission rate literature, which again is used across a ton of settings, hasn't perfectly nailed down. I think there's a lot of more work that could be done on both of those. So step one was I wanted to estimate the scale effect. Promise I won't dwell on the econometrics very long. This is the model. I'll show you pictures. What am I doing here? I'm taking the hourly aggregate emissions from all of the fossil fuel generators in a specific region. That's ET. And I'm going to regress that on a function of the total fossil fuel generation that comes from the generators in that region during that same hour. Effectively, what I'm trying to do is come up with just a simple relationship between how much pollution comes from the fossil fuel generators given how much they're generating. What does this look like? The red line in this top figure is that function there for the Texas region for CO2. As the level of fossil fuel generation in Texas increases, not surprisingly, the level of CO2 emitted by those fossil fuel generators goes up. Okay? What I'm really interested in is the slope of this function. Okay? It looks pretty linear for CO2, and that tells me there's not much difference in the marginal emission rate across different levels of generation in the Texas market for CO2. An extra megawatt hour of fossil output is going to produce pretty much a constant increase in CO2. That's not the case for, that looks like, SO2 in the Texas market. And this is intuitive, right? At really low levels of fossil generation, the fuel that's on the margin is much more heavily coal. So increasing fossil generation leads to big increases in SO2. Once you get to really high levels of fossil generation, gas is mainly on the margin. And gas doesn't create much SO2, so increasing fossil generation doesn't do much to the SO2 emissions. NOx, well, you see there's some really inefficient NOx, or natural gas units that come online at really high levels of fossil generation, so the slope gets steeper. Okay? All I'm interested in is what does this function look like in different regions. Okay? A couple important things to see. The slope in this region, that was the one that had Ohio, for example, is on average higher for each and every pollutant compared to the Texas market. And that's important, again, because, well, this region gets a lot of its electricity from coal. Coal is on the margin pretty much during all hours, to some extent at least. That's not true in Texas. So the marginal emission rate literature has gone on and said, plugging an electric vehicle in this region would create a lot more pollution than plugging that electric vehicle into the grid in this region. Or generating renewable electricity would be much more beneficial in this region as opposed to this region. Okay? That's all just the scale effects though, right? So how do we estimate the scale effect from this stuff? Well, I observe the fossil generation that occurs at time t. And if I'm saying we're going to add more renewable output during that hour, and that's the amount of renewable output I simulated, I just made up, then we're saying, look, the fossil generation that's required goes from this amount to this amount if we were to add renewable output. And that means that the emissions went from this amount, that predicted function up there, to that function evaluated at a lower level of fossil generation. So by adding this extra renewable output, I'm pushing down the amount of pollution that I'm emitting. And the difference between those is how much pollution I'm guessing we've reduced. And if I aggregate that up across every hour during 2009, now I have an estimate of what was the change in the annual emissions caused by adding this sequence of renewable outputs. Does that make sense? Sort of? Yeah? Nodding somewhat? Okay. Really big assumption in there, and it's important to highlight. That function that I've estimated, I'm assuming it's not changing. When I add renewable electricity, that function stayed the same. That's been ignored by this marginal emission rate literature, but I want to point out that's a really important assumption. What determines the shape of that function? It's what fossil fuel plants are in that region and what order are they dispatched in, right? we saw the coal plants were dispatched first. That's what made the SO2 function rise really steeply to start with, and then gas came online and it flattened out. I'm assuming the shape of that function doesn't change, which means I'm assuming the fossil fuel generators are still being dispatched in the same order. For that to be true, there can't be any changes in their input prices. If the price of NOx fell quite a bit, then plants with really high NOx emission rates might actually move lower in the dispatch order and be affecting the marginal emission rates at a much lower level of generation. Right? So what am I assuming when I'm doing this? I'm assuming NOx prices don't change. I'm also assuming fuel prices don't change. To be fully fair, I'm also assuming wholesale electricity prices don't change. I'm assuming a lot of things that aren't changing, and that's fine, but we have to be upfront about what we're estimating. We're estimating a scale effect. Kind of like a partial equilibrium effect. It's saying nothing else changed other than that amount of renewable output. And if we do that, we can estimate the change in pollution. In levels, they're big numbers. I don't like to think in levels. I like to think in averages. So this is the average reduction in CO2 that would occur for each megawatt hour of solar output that we add. So we'd offset 0.63 tons of CO2 for each megawatt hour of solar, 0.7 pounds of SO2, 0.88 pounds of NOx. If you had added that solar to the mid-Atlantic region, where there's a lot more coal, you're going to offset a lot more CO2 with this scale effect, and a lot more SO2. Almost twice as much NOx, it looks like. Okay? This is where the literature is completely stopped. Full breaks. I keep harping on that. I'm part of that too. I kept making the same mistake over and over in my research. These are estimates of half of the story, is my argument. Okay? So going back to that model, what have we estimated? We increased renewable output and we shifted back to B. And I said, yeah, you got big reductions in CO2, SO2, and NOx. I agree. That's the scale effect. But if we really think that NOx cap is going to be binding, we're not going to stay at B. We're going to have to shift back to that level curve of NOx, the red line, in which case, is it possible that we have not reduced the level of this unregulated pollutant, the blue one, but increased it? So we need to estimate the impact of this movement from B to C now. That's really hard to do. I don't think I've done a very good job of it, but I'm going to give you some hand-wavy evidence that I think moving from B to C would cause a pretty meaningful increase in these unregulated pollutants. Okay? So what is that movement from B to C again? It's a reduction in the price of NOx permits. So I want to ask the question, well, how much would emissions change if the NOx prices fell? That'd be really hard to estimate empirically because a lot of these changes in NOx prices that you'd see aren't just random shocks. They're completely endogenous changes in the price of NOx. So anyone who's taken an econometrics course would know putting emissions on the left-hand side with NOx price on the right-hand side could be a big problem. Right? So what I'm going to do is exploit the fact that, remember, there was 2 NOx cap and trade programs. There was the annual one, and then at the start of May each year, the price of emitting NOx jumps way up in some years. Well, I shouldn't say in some, in the first year. After that, the change in the price of emitting NOx during the ozone season was actually really low because it wasn't a very binding policy. So what I'm going to focus on is this small window of time right here. That's a pretty unique little period of time. For a coal unit, for kind of the median coal unit in my sample, they were plugging along thinking that the price of emitting NOx was about $1.50 per megawatt hour. And then the very first day of the ozone season, that jumps up to $2.10, $2.15 per megawatt hour. Not a very big change. It represents maybe about a 5% change in their variable costs of generating, but perhaps big enough to change where they would fall in the dispatch order, right? Perhaps big enough to change whether they're operating or not. Perhaps, right? I'm going to use that shock to the cost of emitting NOx to try to answer that question I wanted to know, which was, how much do emissions change if the price of NOx were to change? Does that make sense? This is just called an event study. What I'm going to do is focus on a small window of time around that beginning of the ozone season. 10 days before, 10 days after in this case that I'm going to show you. The blue dots are plotting the hourly fossil generation and the hourly emissions in the 10 days right before the ozone season started. The red circles are the pollution emitted as a function of the fossil generation in the 10 days right after the ozone season started. So if the NOx price jumps up at the start of the ozone season, and we see these lines effectively shift down a little bit, that's telling me that pollution fell when NOx prices rose. Or vice versa, if NOx prices were to fall, I'd argue that means pollution would go up, which is that composition effect that we would like to avoid. But so if you squint at this, you certainly see evidence that it fell with the increase in NOx prices for SO2. There's perhaps a little bit of evidence for CO2. It's pretty noisy with NOx, as it turns out. Okay. I want to actually estimate that. I want to know on average how much did this line shift down, if at all, when NOx prices went up. That's what the event study is doing. It's controlling for the level of fossil generation during hour T and asking how much did the emissions change during that hour after the start of ozone season. So the ozone season here is just an indicator. It's a variable that goes from 0 to 1 the first day that this ozone season starts. Okay. If alpha is negative, that means NOx prices go up, pollution falls. Right? Or vice versa, if NOx prices fall, pollution is going to go up, which is that bad composition effect again. When I estimate that, sure enough, there's pretty strong evidence that alpha is negative for each of those three pollutants. So what that's telling me is, yeah, if NOx prices fall, we're going to re-increase each of these different pollutants by some amount. What's important is to think about the ratios of those alphas. What the ratios of those are saying is, look, for every extra 1 pound of NOx, you have to re-increase. Right? So NOx prices fall, you're going to re-increase NOx emissions. For every 1 pound increase in NOx, you're going to increase CO2 by 1.15 tons, and you're going to increase SO2 by 5.39 pounds. That's my best guess. Okay? So I can use those now to say, let's go beyond this little scale effect estimate, which the marginal emission rate literature has said. Right? We saw earlier, if you added solar to Texas, you were offsetting 0.63 tons of CO2 per megawatt hour. 0.88 pounds of NOx per megawatt hour. But on net, if we really think this cap on NOx is binding, we shouldn't be offsetting any NOx. How much are we changing these other unregulated pollutants then? Well, here's my calculation. It's the sum of the scale effect and the composition effect. The scale effect we already estimated. The composition effect is, how much does NOx have to re-increase to get back to a binding cap? And as it re-increases, how much are you going to re-increase CO2? And how much are you going to re-increase SO2? This is literally taking that movement from B to C and just putting it into numbers. And when you look at that, on net, I'd find that you still reduce some CO2 by adding solar to both of these regions. But you're reducing a lot less CO2 than you would have expected if you ignored this interaction with the cap and trade program. We thought we were getting pretty reasonable reductions in SO2, but darn if this isn't saying, no, we should actually get annual increases in SO2 because we're adding renewables in that region. Does that make sense? It's not ideal. Now the flip of this, going back to say, how does this mean anything for, say, electric vehicles? I would say the exact opposite pattern would then hold. When you plug in an electric vehicle, you're going to increase demand for electricity. This would not be a negative, it would be a positive. So for every 1 extra megawatt hour of electricity demanded to charge your car, let's say you're increasing CO2 by 0.8 tons in the RFC region. But now, look, we've increased the emissions, therefore we should put upward pressure on the price of the NOx permits. That increase in the pressure, NOx prices going up, what should that do? The composition effect should push the pollution back down. So the same intuition I'm using to argue that renewables are offsetting less pollution than we thought can actually flip and say, look, electric vehicles, plugging them in regions with a cap and trade program are creating much less pollution than the marginal emission rate literature has argued. Does that make sense? Yeah, I think you can, and I think you should. I think a lot of the same intuition is going to carry over where you have positive correlation in the emission rates across these different pollutants. The same intuition should hold that the composition effect should move against the scale effect. So here's kind of the policy takeaways then. Look, if we're going to have a cap on a set of pollutants, and then we're going to have a bunch of unregulated pollutants. And we're going to use those unregulated pollutants to say, well, look, I haven't done anything to CO2 in this region. That justifies me subsidizing renewables. I'd argue that the external benefit of renewables in that setting could be quite small, and that those subsidies for, say, renewables are a really bad policy. Not at all a good substitute for missing prices on the unregulated pollutants. There's a bunch of other related questions then. So if we had a tax on NOx emissions during this time period instead of a cap and trade program, then this composition effect never occurs because there's no permit prices that endogenously change. In other words, only the scale effect occurs, and in which case renewables look like they provide a really big external benefit, and that's a case where a subsidy for renewables is quite justified. So intuitively, I guess this would say, trying to overlap these policies together can create some pretty bizarre situations. We should be putting prices on each pollutant, clearly to start with. But if we can't do that, these results provide a pretty clear argument for why taxes, where we avoid any of these endogenous composition effects, might be a pretty attractive thing, as opposed to a cap and trade program. The word taxes clearly is not one of the favorite words in the US. So if we can't use taxes, there's a lot of different policies that we can effectively layer on top of our cap and trade programs to prevent or mitigate this composition effect. My favorite would be price collars. What are price collars? They're floors and ceilings on how high or low the pollution permit prices can get. If you set really narrow price collars, there's only so much composition effect that could occur before you're at the price floor for those permits, and there's no more composition effect occurring. Does this apply to California right now, where we have a cap and trade program for CO2? I would argue our policy is not binding. Our permits are at the price floor of our price collar, so therefore in California, we should not be concerned about this composition effect. But if we get to a point where we're at a binding CO2 cap and the pollution permit prices are in between the ceiling and the floor, that's a setting where this composition effect becomes really relevant. Okay? That's all I've got. There's the conclusion slide. I'd love to hear questions. Appreciate all you staying awake, entertaining me. depends on the pricing structure. So the question is, if we change pricing in California's retail side, how would that affect this this setting? So if we were to go to time of use pricing, where essentially we're still keeping the price from one day to the next during a specific hour constant. So the 6 p.m. price today will be the 6 p.m. price tomorrow, will be the 6 p.m. price yesterday, yada, yada, the same. In that case, that time of use pricing should just redistribute our demand patterns, right? That's not going to actually mean that our consumption is responding to the level of solar output in the short run. If today happened to be a really sunny day and produced a lot more solar, and the wholesale electricity prices were much lower, that doesn't get fed back through to time of use pricing, in the short run at least. Therefore, our consumption pattern shouldn't actually respond to solar, and nothing actually changes in this setting. Now, if we were to have real-time pricing where our retail rates were directly tied to the actual daily and hour-specific wholesale prices through some mechanism, and we actually responded to that, there's a lot of ifs there, right? I personally wouldn't respond to it because I don't use a ton of electricity, and I don't actually put forth enough effort mentally to think about what would the price be during this hour, should I turn off my TV or not. If everyone's not like me, if everyone's much more rational and they're actually changing their electricity consumption patterns based on real-time prices, which are tied to wholesale prices, then this story gets even more complicated, because now you have a positive price elasticity, and I've assumed we're perfectly inelastic in this world. In that case, well, if you add more solar electricity, you should push down wholesale prices, you should push down retail prices. That should increase demand. So therefore, a megawatt hour of solar is not going to offset a megawatt hour of fossil fuel output. It might only offset 0.8 megawatt hours of solar. So in that case, that's another example where just thinking about the scale effect is going to misinterpret what the actual net effect on pollution might be.
Binding constraint. What does this look like in the context of one sector's consumption of carbon
One sectors? So do you want to move to multiple sectors?
So I
because
guess what I'm saying is, in the context of an electric vehicle, you're taking your emissions out of the oil sector or out of the petroleum sector and into the electric sector. The cap remains the same. How should we think about that impact?
there's a lot of levels there I have not thought through. There's a,
It's a big question, I know. But is there anything that should we just think about the cap is going to be the level of carbon emissions, no matter who does what where, ultimately
yeah.
emit that level of carbon?
Bringing in the oil element scared me. But I guess, when you think about it, this was specifically looking at electricity sector. But if you really wanted to think about the California case, let's say a cap on CO2. That cap applies to the electricity sector, the industrial sector, perhaps the dairy sector, who knows eventually, right? We could be going down a road where a bunch of different sectors are responding to this CO2 permit price. In which case, if you add more renewable electricity into California, say 50% of our output, you should be pushing that CO2 permit price down. In which case, you should be endogenously changing decisions, not just in the electricity sector, but in the oil sector, for example. Maybe now the CO2 permit price has dropped. If that's directly altering the way refineries want to think about how much E85 they sell versus E10, could push them towards purchasing and bringing less E85 into California. There's all of these feedback effects when you start linking these policies. And if you just look at one at a time, you ignore all of those feedbacks, and that can be pretty dangerous, I guess is my argument. I still have to think about all of the possible interactions there. I don't have a good answer.
Sometimes I've seen gasoline vehicles. Some dynamics in the electric
It's very complicated. That's why you should hesitate when you grab onto one estimate that's completely ignored all of that complication, for sure.
permit market is functioning.
It's, by the end of that CARE program, it was a pretty much ineffective policy in the sense that the NOx permits dramatically exceeded the amount of NOx that was being emitted, and you can think of a whole slew of reasons why that could be. Natural gas got a lot cheaper during that period. We experienced a mild recession during that period. A lot of things occurred to make that not a binding policy. During the earlier stages of the NOx cap and trade programs in the East, it was a really pretty fluid market. It was pretty efficient. But now your question of, could there be something that make the impacts of perhaps that composition effect in some sense delayed or spread out over time? There's certainly a big one, which is you can bank these permits. So if I had an extra permit that I didn't need to use because I didn't need to generate that electricity because someone put a solar panel in the market, maybe I can save that permit and then use it 2 years later and emit that pollution then. So that composition effect could bleed across years in these cap and trade programs. But that's an important thing to kind of internalize. For something like CO2, doesn't matter much. For something like NOx, that could be really important if you're pushing all the pollution into one period as opposed to another. What's the third one then?
So the third thing I guess would be technology change in the background. Like, so we're on this trajectory where technology is changing a lot, and so that's also changing what's at the margins in this picture, right? So I'm kind of wondering how we talked about price policy maybe changing, technology changing at the margin of the electricity sector, how that
Those pictures are all conditional on the set of technologies that are in the market at that time. And they're conditional on the input prices like coal prices and gas prices and everything at that time. As technology changes, to me the biggest one has been fracking, right? As we have changes in technology, makes natural gas much cheaper, completely flip-flops the ordering of those marginal emission rate pictures around. Those numbers are all going to change dramatically, but the intuition that there's still this composition effect that could arise doesn't change. Now, that's to say, technology, you brought up another point, which is things are improving, technology is getting better. That in and of itself is a really good argument for subsidizing something like solar or wind. If you think there are big spillover benefits to getting these things out in the market, learning how they work, and then taking that knowledge and everyone else can benefit from it. This hasn't touched on that kind of externality benefit one bit. Yeah. Certainly an important thing to think about in terms of policies. It's sunny out. It's Friday. I appreciate it. Thank you, everyone. Have a great weekend.